So, we still had this example on Friday to finish up, so let's finish that up first. It was for a second order system, and it's an example from my research. So, in magnetic resonance force microscopy, or MRFM for a mouthful of short, the primary detector is a small cantilever beam with a magnetic tip. Model the beam as a spring mass damper system with mass of 6 picograms, spring constant 15 millinewtons per meter, and damping coefficient given there. Magnetic input forces on the beam, U of t, are applied directly to the magnetic tip. That is, a Newtonian force analysis yields the input-output ODE given here. So we don't have to derive that ODE. I'm giving it to you. You could do our linear graph modeling technique on a spring mass damper system with a force applied directly to the mass, and you would get the same input-output differential equation. So I did that part. You could also just sum the forces, which is another way. It's a little bit quicker in some cases, like the simple system like this. Summing the forces gets you to this result pretty quickly. So it gets us this input-output ODE, where y is the motion of the tip, the displacement of the tip of the cantilever. So it's a pretty good model. It's not perfect. It doesn't deal with higher order modes of the cantilever beam, but that's something you guys will talk about in vibrations class. This is something that is very common to do, though. Typically, we only care about the second order characteristics of one of these systems. So good. So I asked 4 questions. What is the natural frequency of the system? What is the damping ratio? I also tell us to find the free response for given initial conditions, and the forced response, the impulse forced response for a 3 scaling of the unit impulse function of the Dirac delta function. So these are the, and there's a 5th thing too. Find the total response for the initial condition and forcing from above if they're both applied. So let's take this one at a time. So I need to find the natural frequency and the damping ratio first. And remember, we can use the form of the equation, the standard form of the equation, to identify what the natural frequency and damping ratio is, or what they are. Plus omega n squared y equals some forcing function, right? So that is the standard form for a second order system, and this is the form that kind of defines for us what zeta and omega n will be for a given system. So if we compare this standard form to the form that's given, we have this coefficient m out here in front of y double dot that we have to divide through in order to make that unity, right? So if we divide both sides of the equation by m, we get y double dot plus, and now that's coefficient is 1 because m over m is 1, plus b over m y dot plus k over m y equals 1 over m u of t, right? So that's our equation. So what we can do is we can just equate the coefficients. So the y dot coefficient. So now that we've got unity here, we can say, okay, this term must be equal to this term, and this term must be equal, the y term must be equal to the y term in this equation. So we get two equations, and we have two unknowns. We want to know what zeta and omega n are in terms of our system parameters, b, k, and m. So the easiest one is from the last coefficient, the y coefficient. That gives us omega n directly. So from this, we get that omega n squared equals k over m. And solving for omega n and taking only the positive side, because natural frequencies are taken to always be positive in our work. So the natural frequency is k over m, square root of that. Okay, so that's our first answer. Omega n is the square root of k over m. Good. And this is a result you're going to get really familiar with when you get into vibrations class. This is the natural frequency of any second order mechanical system in a common configuration, at least. Spring mass damper system. So now we've got part 2, which we can actually use some of the results of part 1 to help us with. So we can, in part 2, we're supposed to find the damping ratio, zeta, right? So we found what omega n is, and now we need to find what zeta is. We have this other equality here, so let's just use that. And we can say that 2 zeta omega n is equal to b over m, which, if we solve that for zeta, gives us b over 2 omega n m, which, if we plug omega n in, is b over 2 square root k over m times m. So we have an m to the negative 1/2 and an m to the 1 in this denominator here. So let's continue to write what this is equal to. Simplify this a bit. We get b over 2 square root. There's k square root, and then there's an m square root. So of k m. So that's our zeta in terms of our original parameters, b, k, and m. So that's good. We've got that. Now we're on part 3. So whenever you have a second order system, this is going to be typically the process we're going to use. We're going to want to know what the damping ratio and natural frequency are. They're interesting in and of themselves. Knowing what the natural frequency is tells you about which frequency it's going to oscillate at. If you release a second order system, an underdamped second order system from rest, it's going to oscillate at that frequency, or approximately. And zeta, knowing zeta tells you a lot of information. For instance, is it overdamped, underdamped, etc. So we're interested to know what zeta is for a lot of reasons, and so that gives it to us. Very good. So we've got 1 and 2. So now we're on 3. So we need to find the free response for initial condition. We displace it by 10 nanometers, the cantilever, and we let it go. And we want to see what happens to the response. So we're going to start off at 0 velocity and see how it responds. So the free response, we developed a free response solution up here, right? These are all forced response, all the way back up here. We developed it, but we need to know what zeta is in order to know which solution applies, right? So we need to compute what zeta is for this problem. We have numbers, right? So we need to actually plug them in. So let's do that. So way back down here. we have numbers. And let's plug in what zeta is. And I actually have that computed, I think. So we don't have to plug it in live. Yeah, it's 5 times 10 to the negative 5. 5e negative 5. That's like engineering calculator notation, right? Is that okay? Does that freak you guys out? It's okay.
Isn't it usually a capital E?
Sometimes. I don't know. I don't use calculators. In MATLAB, you can just type E. So that's why that E negative 5. That does look more right, though. I think you're right. Okay. Cool. So that is. So what do we have? We have. Is the system stable? Is it unstable? What do we have?
It's above.
It's above 0. So that means it's stable, right? So it's positive. So if you go back up to this list of different possibilities, if zeta is less than 1 or less than 0, then it's unstable. So it's not less than 0. It's not 0. It's greater than 0. So it's not undamped. It is underdamped. It's between 0 and 1. So these are our lambda 1 and lambda 2. This is our damped natural frequency. And the preferred form of the free response that we're going to like is given there. So let's go ahead and just use that guy, 611, as our free response. This did conveniently use y dot of 0 equals 0. So that's nice. We don't have to go back and find the free response from scratch. So we get to use this value. So 611 tells us that we can use, so I'll say from 611, we have that y free of t is equal to y naught, which is 10 nanometers. I'm just gonna leave it as y of 0. We know that's 10 nanometers, but we don't really want to write that out. It's just so hard. And then times, I'm not going to keep scrolling up here. I'll just look in my notes. Times this fraction, like not taking my own advice and keeping my notes clearly organized. So what do you know? This is the exponential e to the negative zeta omega n t. We know what zeta and omega n are, so we could compute what omega n is. I didn't compute it above, but you could just plug in the numbers and compute it. And cosine, the only one you need to compute is zeta in terms of like knowing which solution you need. Omega d t plus psi, where omega d is equal to, by definition, the natural frequency omega n scaled by this factor that is zeta, or no, 1 minus zeta squared. So, and we have psi from equation 612 as being negative arctangent of zeta over the square root of 1 minus zeta squared. So this is the solution. So that's our free response. Cool. Didn't have to do it from scratch. It's nice. And then the next question. So 3, that was 3. And then 4, find the impulse response for the scaled delta function. So let's go to our table here. We have an underdamped case, right? We are between 0 and 1 with our zeta. And we have, let's look at the characteristic response for a delta function. Now we're going to scale that delta function by 3, but we can use superposition to fix that. So if we know what happens when you put in delta, then we can find out what happens when you put in 3 times delta pretty easily. So the characteristic response is given here. So let's write that down. So for characteristic response is, so I guess I'll put in parentheses, forcing function just being equal to delta. Whoops, that was not a delta. T. From table 6.2. Gives us that, I'll call it y sub ch for characteristic response, is equal to, looks like e to the negative zeta omega nt divided by omega n times the square root of 1 minus zeta squared, which is actually just the damped natural frequency, times sine of the damped natural frequency t. So using superposition, we can find that y forced of t, since we multiplied the Dirac delta function, our actual forcing function is 3 delta. We can just multiply the output by delta. So we have 3. I'm just going to write 3 ych of t because I don't want to rewrite all that. Does that sound good to you guys? Sweet. Okay. Guys ready? It's the last part. We got this. I believe in us. Okay. 5. We need to find the response to the initial condition and forcing from above if they're both applied. So you have an initial condition of 10 nanometers offset and you have a 3 delta impulse input. So we can use superposition again to find the result. So again, applying superposition. We can say that our y of t is equal to y free of t plus y forced of t, which, I mean, is the answer, because we already defined what both of those are, but yeah, we don't need to write it out, right? Y free and y forced are already defined. So here's my y forced, here's my y free. So that's the response. And that response, I mean, it's totally doable. We could go back to our method of undetermined coefficients, solve this problem out good old-fashioned way, would be totally fine. But this wasn't too bad. This took us 20-ish minutes to do it this way. The other way would probably take us, if we didn't make any mistakes, it'd probably take us like an hour. And if we made a mistake, it would probably take us multiple hours, right, to do it. So it's pretty nice, and it's already in a form that's pretty easy to understand. We're going to have these sinusoids that are added together, and you have these decaying exponentials, and yeah, pretty easy to understand what it looks like. Whereas when you get it, if you go through the other process, you're going to end up with a bunch of complex exponentials, and probably you would need to convert that into a trigonometric form before you would have a good feel for it. So I'm not saying that it would be a bad way to go, it's just a longer way to go. So that's why I'm advocating the use of these tables with superposition and the differentiation property. Okay? Cool. All right, so this is the end of the chapter. So are there any questions on like how to go about using these solution techniques? Yeah?
Well, we have the tables on the text.
Absolutely, because they're in your notes.
Okay.
Well, I'm not going to give you the tables, but you can bring the tables. I know something's going to show up without the tables. Bring the tables. Yes?
So this is similar to what our homework problems are, just we might have to derive some of the ODEs.
Yeah, so actually in the chapter 9 homework problems, so this week's homework is going to, well, I would encourage you to use the tables on this week's homework. So last week's homework, you used superposition, but you had to still derive those solutions from scratch, unless you use the tables, and this is fine. But this week, chapter 9 homework, I'm encouraging you to use the tables to solve the problems. It would be a faster way to go. So, yeah. So yeah, you get some practice on that. So the homework due Friday and the quiz on Friday will be over that. The first homework solution is posted, by the way. Okay. Anything else? All right, good.